Hello everyone, this is Solved by Hand channel. I hope that you are doing well and that you are ready to watch a new video from Solved by Hand channel. In the video today we will talk about thermodynamics. So in this video we'll see part 1. So we'll see part 1 of chapter summary 1. So we will see part 1 of chapter summary 1 of thermodynamics. So we'll see part 1 of chapter summary 1 of thermodynamics. Part 1 of chapter summary 1 is about internal energy, kinetic energy, potential energy, and total energy. So, without any further delay, let's go to our paper and start moving our pen. So in the part of today, which is part 1, so today, part 1, we can say that the sum of all forms of energy of a system is called total energy. Which consists of internal, kinetic, and potential energy for simple compressible systems. So we can say that the sum of all forms of energy of a system is called total energy. So this is the sum of all forms of energy of the sum of all forms of energy of a system is called total energy. So we have just said that the sum of all forms of energy of a system is called total energy, which consists of internal, kinetic, and potential energy for simple compressible systems. So to explain this, we will start by speaking about internal energy. So let's speak about internal energy. So we'll explain what is internal energy here. So we'll write note 1. In note 1 we can say that note 1, and I will highlight this note 1. In note 1 we can say that internal energy represents the molecular energy of a system and may exist in sensible, latent, chemical, and nuclear forms. Internal energy was defined earlier as the sum of all the microscopic forms of energy of a system. It is related to the molecular structure and the degree of molecular activity and can be viewed as the sum of kinetic and potential energies of the molecules. So let's read again this to understand it. So we can say that internal energy represents the molecular energy of a system and may exist in sensible, latent, chemical, and hormonal. So internal energy represents the molecular energy of a system and may exist in sensible, latent, chemical, and nuclear forms. Also, we can say that internal energy was defined earlier as the sum of all the microscopic forms of energy of a system. And internal energy was defined earlier as the sum of all the microscopic forms of energy of a system. It is related to the molecular structure and the degree of molecular activity. It is related to the molecular structure and the degree of molecular activity, and can be viewed as the sum of kinetic and potential energies of the molecules. So this is all that we can say about internal energy for now. So that was about internal energy here. So let's speak about another term, which is kinetic energy. So in note 2 we'll speak about kinetic energy. I will highlight note 2. So about internal energy, we can say that the energy that a system possesses, so the energy that a system possesses as a result of its motion relative to some reference frame is called kinetic energy. And to distinguish kinetic energy, we use the abbreviation KE. So this is the abbreviation of kinetic energy. When all parts of a system move with the same velocity, the kinetic energy is expressed as. So let's read this again. The energy that a system possesses as a result of its motion relative to some reference frame. So the energy that a system possesses as a result of its motion relative to some reference frame is called kinetic energy, and we use the abbreviation capital K with capital E. Also, we can say that when all parts of a system move with the same velocity, the kinetic energy is expressed as. And so we'll see the formula that we use for the calculation of the kinetic energy. So we use this formula. Can use this formula. We'll write KE is equal to m times v squared divided by 2, and the unit that we use here is kilojoule, kj, which is the abbreviation for kilojoule. Or on unit mass basis, we can write small k, small e. So also here we are speaking about kinetic energy, but on a unit mass basis. So here we are speaking about kinetic energy on unit mass basis, so which means kinetic energy per kilogram. So we use, to abbreviate this, we use small k with small e, and we use the formula. It is equal to v squared divided by 2, and the unit that we use here for the kinetic energy per unit mass, the unit that we use here is kilojoule per kilogram. So that was about the formulas that we use for the calculation of the kinetic energy. So in these formulas, m that we see here, so the m that we see here designates the mass. So this one is the mass, and the unit of the mass is kilogram, and the v that we see here is the velocity. The unit of the velocity is meter per second, and the same thing for here. So for here, the same thing, v is velocity in meter per second. So that was about the formula that we use for the calculation of the kinetic energy. And the kinetic energy per unit mass. So this one has the unit of kilojoule, and this one has the unit of kilojoule per kilogram. And this formula we can see the mass m, and in this formula we don't use the mass, we use only the speed squared divided by 2, and the unit is kilojoule per kilogram. And we can add another part of this node too, and we can add, so this we have plus here, so I can add another plus to designate another part of node 2. So in the second part of node 2, I can talk about the kinetic energy of a rotating solid. So here I will write another plus, and I can say that the kinetic energy of a rotating solid body is, so here we can use the formula, we use another formula. When we have a rotating body, we use another formula to calculate the kinetic energy. We use this formula. Always we use Ke to designate kinetic energy, but for a rotating body we use this formula: 1/2 times I times omega squared. And what is I and what is omega in this formula? So I designate moment of inertia of the body. So the I that we see in this formula is the moment of inertia of the body. And what is omega? So the omega that we see here is the angular velocity. So in the case of a rotating body, the I plays the role of the mass. So instead of the mass, we use the I, we use the moment of inertia, and omega plays the role of the velocity. So instead of the velocity that we used in another formula, we use omega, which is the angular velocity. So this is the only difference between kinetic energy of rotating solid body and translating solid body. So let's go to another note. But before to move into note 3 of this video, before moving to note 3, let's give an example about kinetic energy. So we'll use example 1. So let's write example 1. So this is example 1. So in our example, we can have a surface like this, and we can have a body that has a form of a box. So for example, a box, we can have a box like this. The body, so it has center of gravity here, and it moves with the speed v1. Also, this body has a mass m1. So for this body, we can calculate the kinetic energy using the formulas that we have seen. So to calculate the kinetic energy for this body, we can use the formula, and we can write Ke is equal to 1 over 2 times m1 times v1 squared, and unit here will be kilojoule. So the mass m1 that we see here is the mass of the body that we see here, m1, and v1, the velocity of the body that we see here, is the velocity that we can see here. Also, per unit mass, if we want to calculate the kinetic energy per unit mass of this body, we can write another formula, or per unit mass we can write small k, small e, so for to calculate the kinetic energy per unit mass, and it will give us, for the formula, 1 over 2 v1 squared, and the unit here will be kilojoule per kilogram. And the speed that we see here, so this is v1, that is the same one that we see here, v1. And we don't use mass. We don't use mass in this formula, because here in this formula we are speaking about the kinetic energy per unit mass. So in this formula we don't use the mass m1. So this is said. Let's move to note 3. So let's speak about note 3. So note 3, and I will highlight note 3. So in note 3 we speak about potential energy. So let's speak about potential energy. We can say that the energy that a system possesses as a result of its elevation in a gravitational field is called potential energy, and we use the abbreviation big capital P with capital E. And potential energy can be expressed and is expressed as, so we'll see the form. So but before seeing the formula, let's see again what we wrote in our in note 3. So in note 3 we wrote that the energy that a system possesses as a result of its elevation. So as a result of its elevation, so potential energy is due to the elevation. So the energy that a system possesses as a result of its elevation in a gravitational field is called potential energy, and we use the abbreviation PE. So this is potential energy. So the potential energy is due to the elevation. Now we will see the formula that we use for the calculation of the potential energy. So we'll use the formula. The formula that we use is PE is equal to M times times J times Z, and the unit that we use for calculation, the unit that we use here is kilojoule, or on unit mass basis we can use the formula small p with small e is equal to J times Z, and the units that we use here, the unit used here is kilojoule per kilogram. So let's look again at these two formulas that we wrote here. So in these formulas, the M that we see here is the mass. Its unit can be kilogram. The J that we see here is gravitational. The gravitational acceleration. Its unit is meter per second squared, and normally we use as value, we use for the value of the J, we use the value 9.81 meter per second squared. So, and the Z that we see here, so the Z that we see here, what is the Z? The Z is the elevation of the center of gravity, and for this elevation of the center of gravity we use the unit meter, so meters in meters. So this is the formula that we use for the calculation of the potential energy. The potential energy is equal to M, which is the mass, times J, which is the gravitational acceleration, times Z, which is elevation of the center of gravity in meters. Also, we can calculate the potential energy per unit mass, which means we can calculate the potential energy per kilogram. So to calculate it, we use this formula: small p with small e equal J times Z. So in this second formula, we don't use the mass that we see here. We don't use it. We use simply small p, small e, which is potential energy per unit mass, is equal to J, which is the acceleration of gravity, times Z, which is the elevation. And the unit here, the unit is kilojoule per kilogram, because here we are calculating the potential energy per unit mass. So the unit here is kilojoule per kilogram. So let's see an example about this. We will see an example about calculation of potential energy. So let's see an example about this. So that will be example number 2. Let's see example 2. So in example 2, I will write example 2, example 2. So for example 2, I will take the example of a mountain. Let's suppose that we have a mountain like this. It has this form. So this is our mountain. And on this mountain we have a body. So I will draw a body. So I have a box. For example, we have a box. It has a center of gravity here. Our box has a mass that we can call mass 2. It has mass 2. So this is our box. It has mass 2, and it has an elevation. It has an elevation of Z2. So it has mass which is equal to m2, and it has an elevation. The center of gravity of the box, it has an elevation of Z2. So how can we calculate the potential energy of our box? How we can do that? So to calculate the potential, how we can calculate the potential energy of our box? So to do this, we can use the formulas. So the potential energy will be equal to P E is equal to m2, which is the mass of our box, times g, which is the acceleration of gravity, times z2 that we see here, which is the elevation of the center of gravity of our box. And units that we will use, that we will have in your calculation, is kilojoule. We can also calculate the potential energy of the box per unit mass. So, or on unit mass, we can use the formula. So small p with small e is equal g times j times z2. So we don't use in per unit mass to calculate the potential energy per unit mass. We don't use the mass m2. We use simply j times z2. J, which is the acceleration of gravity, times z2, which is the elevation of the box. And here so here we have kilojoule, and here for after calculation we have as unit, we have units of kilojoule per kilogram. So our example is done. So this was about our example. So we have finished our example. So let's continue. We'll continue with note 4. So we'll speak now about note 4. So let's speak about note 4. We'll go to note 4, and I will highlight this note 4. So in note 4 that you can say that closed system whose velocity and elevation of the center of gravity remain I did a mistake here, so I jumped one thing, so I have to correct this. So normally in note 4 I have to write this, so note 4, and I will highlight. I will cross out this. So sorry, note 4. Normally in note 4 we should write this. The magnetic. So the magnetic, electric, and surface tension effects are significant in some specialized cases. Only, and are usually ignored. So I will read this sentence again. So in this sentence, the magnetic, electric, and surface tension effects are significant in some specialized cases only, and are usually ignored. So they are usually ignored. In the absence of such effects, in the absence of such effects, which means in the absence of magnetic, electric, and surface tension, so in the absence of such effects, the total energy of a system consists of kinetic, potential, and internal energies, and is expressed as. So here in this sentence I am speaking about a new kind of energy that we call total energy. So in this sentence we have seen that in the absence of such effects, which means in the absence of magnetic, electric, and surface tension, so in the absence of such effects, the total energy of a system consists of kinetic, potential, and internal energy. So the total energy of system is formed by kinetic, potential, and internal energies, and is expressed as. So we will see the formula that we use to calculate the total energy. The total energy is formed by kinetic, potential, and internal energy. So we'll see the formula that we use to calculate the total energy. So to calculate the total energy, we use this formula or this relation, the total energy. So for the symbol that we use for the total energy, we use the symbol E. So E, total energy, is equal to big U plus big K, big E, plus big P, big E. and is equal to U plus M V squared divided by 2 plus M times G times Z, and the unit here is kilojoule. So I will explain that. So the E that we see here is the E that we see here is the abbreviation or the symbol that we use for total energy. So we use this symbol. So to designate the total energy, we use the symbol big E. So we have seen in the sentence that it is equal to, it is formed from kinetic, potential, and energy. So here we use E, which is total energy, is equal to U, which is internal energy, plus Ke, which is kinetic energy. So this one is kinetic energy, plus Pe, which is potential energy. And we have seen how to calculate them. So internal energy, U, we have spoken about this. So in note 1 we spoke about internal energy. So U, big U, this is internal energy. Ke, which is kinetic energy, we have seen the formula to calculate it. To calculate it, we use the formula M times V squared divided by 2. And for the calculation of potential energy Pe, we have seen that we use the formula M, which is the mass, times G, which is the acceleration of gravity, times Z, which is the elevation. So we just use the formulas. So U here is here. So Ke, which is kinetic energy, we use this formula, and for potential energy we use this formula M times T times Z. We will continue. Also, for the total energy, we can calculate the total energy per unit mass. So also this we can calculate the total energy per unit mass. So to calculate the total energy per unit mass, we use the symbol small e. We use the symbol small e. So small e is equal to small u plus small k e plus small p e, and is equal to small u plus v squared divided by 2 plus g times z, and the unit is kilojoule per kilogram. Kilojoule per kilogram. And this one that we have seen is total energy per unit mass, which means unit energy, total energy per kilogram. To calculate it, we use small u, which is the internal energy per kilogram. We use also small ke, which is the kinetic energy per kilogram. We use to calculate it, we use the formula v squared divided by 2. We don't use the mass, we don't use it. And here Pe is the potential energy per unit mass. So I will write again to be more precise. This one is internal energy per unit mass. This one is the kinetic energy per unit mass, and the PE that we see here designates the potential energy per unit mass. Here small u is the internal energy per unit mass. We can see it here. And this one is the kinetic energy per unit mass. So kinetic energy per unit mass. To calculate it, we use this formula, v squared divided by 2. And this one that we see here, the PE, is potential energy per unit mass. To calculate it, we use this formula, G times Z. And the unit, of course, the unit of total energy per unit mass, its unit is kilojoule per kilogram. So let's continue. Now we'll continue with note 5. So let's go to, we have finished note 4. We'll go we'll go to note 5. Note 5. I will highlight it. Note 5. In note 5 we can say that a closed system whose velocity and elevation of center of gravity remain constant during a process is often referred to as a stationary system. Here we are speaking about a very important words, or so we are speaking about stationary system. So what is the meaning of stationary system? So when you see stationary system, or when you hear stationary system, what is the meaning of that? What is the meaning of stationary system? So a closed system whose velocity and elevation of center of gravity remain constant during a process is often referred as a stationary system. So when we talk about stationary system, we talk about a system that has velocity constant and elevation of so when we speak about stationary system, we speak about a system that has a constant velocity, whose constant velocity, and the constant elevation of center of gravity. So whenever you hear the words stationary system, that means that the system of which we are talking has a constant velocity and a constant elevation. So that is the meaning of stationary system. A closed system whose velocity and elevation of center of gravity remain constant, so remain constant during a process, is often referred to as the stationary system. So that is the meaning of stationary system. Whenever you go to a problem in thermodynamics and you see in statement of the problem that the system is stationary, that means that this system has a constant velocity and has a constant elevation of center of gravity. Its velocity is constant and the elevation of the center of gravity of this system remains constant. That is the meaning of stationary system. In terms of formulas, this means so if we write the total energy, so the formula for the total energy is equal, so big E is equal to U, which is internal energy, plus K E, which is the kinetic energy, plus P E, which is potential energy, which is equal to, here again, U, which is the internal energy, plus I will replace the kinetic energy with its formula, which is m times v squared divided by 2, and I will replace the potential energy by its formula, which is m times j times z. And here as we have seen in the sentence, stationary system has a constant velocity. So this velocity is constant. So this one is constant. So v velocity is constant. So this means that Ka, which is kinetic energy, is constant. Also, this system has a constant elevation, so a constant elevation of center of gravity, so which means that Z that we see here is constant, and this means that the potential energy here that we see here is constant. So and of course m, which is the mass of the system, is constant. So here we see m, which is the mass, and we see again here the mass is constant, so the mass is constant. So z, which is the elevation, is when it is constant, so it is constant. So this formula is constant, which implies that Pe, which is the potential energy, is constant. Also, when v, which is the velocity, is constant, when it is constant, so this formula is constant, which means that the kinetic energy that we see here is constant. And here we'll speak about note 6. So we'll speak about note 6. We'll go to note 6. In note 6 we can say, so I will highlight note 6, I will highlight it. So in note 6 we can say that the change in the total energy, the change in the total energy, and we use the abbreviation delta E. So the change in the total energy delta E of a stationary system is identical to the change in its internal energy. and here we use the abbreviation delta U. So let's read again this sentence and try to understand it. So what this sentence means. So the change in the total energy, delta E. So the change in the total energy, delta E, of stationary system. So stationary system here, this is a key word. So I think that we should highlight this, stationary system. So this is keyword, stationary system. So the change in the total energy, delta E of a stationary system is identical to the change in its internal energy, delta U. So why we have this? So why we have this? Why delta E? So this, why we have delta E? So the meaning of this sentence is, this sentence means that delta E that we see here is equal to delta U. That is the exact meaning of this sentence. Delta E, which is change in total energy, is equal to delta U, which is the change in internal energy. So why we have this? From where this comes? Why delta E is equal to delta U for a stationary system? Why you have that? For whenever we have a stationary system in a problem, we can consider that delta E is equal to delta U. We can, whenever we have stationary system, we can consider that the change in total energy is equal to the change in internal energy. Why we have that? We will see why this. Just stay with me. Don't skip. Stay tuned to our channel. We'll see why we have this. So if we write delta E, which is the change in total energy. So what is the formula to calculate that? So delta E is equal to E2 minus E1, because we are speaking about change. So we have two states. So we have state 2 and state 1. So delta E is equal to E2 minus E1. And how we calculate E2? So what is E2? E2 is equal to U2 plus KE2 plus PE2. So this is, yes, which is the total energy in state 2 is equal to this formula, which is the internal energy in state 2 plus the kinetic energy in state 2 plus the potential energy in state 2. So this is for E2. Let's go for E1. So minus E1. So how we calculate E1? What is the formula? So the formula is U1 plus KE1 plus PE1, which is potential energy. So this is how we calculate the total energy E1 in state 1. So the total energy in state 1, we calculate it, we can calculate it using this formula. U1, which is the internal energy in state 1, plus KE1, which is the kinetic energy in state 1, plus PE1, which is the potential energy in state 1. And since we have a stationary system, so our system is stationary, so this is the keyword that we have a stationary system. So since we have a stationary system, since our system is stationary, what we can write, so what we can write when we have a system which is stationary, we can write for a system which is stationary, we have seen in note we have seen in note 5 that a system which is stationary have a constant velocity and a constant elevation. What is the meaning of constant velocity? Constant velocity means that kinetic energy of the system is constant. So because we have seen in note 5 that when we have a system which is stationary, that system has constant velocity v and constant elevation. So when v is constant, which this implies that 1/2 m times v squared is constant. This implies that the kinetic energy is constant. Also, constant elevation z. Well, this means that m times z times m times g times z is constant, and this means that the potential energy is constant. So we have to apply this here. So whenever we have a stationary system, it implies this. Constant kinetic energy constant and potential energy constant. So we have to do this. So the potential energy is constant. So this is constant. Also this is constant. So which means that they are equal. So they are equal. So they cancel each other. So this goes with this. So this one constant minus another constant. So this goes to 0. This two values, they cancel each other. Also we have kinetic energy is constant. Also the kinetic energy is constant. So this one is this one kinetic energy is constant here, and the kinetic energy here is constant. This means that these two values, they cancel each other. So this Ke1 is cancelled with Ke2 because both of them, they are constant. So Ke2 minus Ke1, they will give us 0. So for example, if Ke1 has a value of 100 kilojoule, also Ke2 will have 100 kilojoule. And also if Pe1 has 2000 kilojoule, also Pe2 has 2000 kilojoule. So they cancel each other. So at the end, in this expression, so this this expression will become like this. So we have delta E is equal to E2 minus E1. So this one, all these values are cancelled. So this one, and this one. And at the end, in the formula, we will have U2 minus U1. And what is this? Is delta U. So here, delta U. And this is the change in internal energy and this is the change. Sorry, so this is the change in not internal energy, the change in total energy, and this is the change in internal energy. And at the end we have our conclusion. So from all this demonstration we can conclude that whenever we have a stationary system, this implies that delta E is equal to delta U. So in every thermodynamic problem, so in every problem of thermodynamic, whenever you see whenever they tell in the statement of the problem that the system is stationary, automatically you can conclude that delta E, which is the change in total energy, is equal to delta U, which is the change in internal energy. So whenever you go to a problem in thermodynamic and you find that your system is stationary like this, automatically this implies that delta E, which is the change in total energy, is equal to delta U, which is the change in internal energy. So whenever you have stationary system, we have the change of the total energy, delta E, is equal to delta U, which is the change in internal energy. Okay, so this note finishes this part of chapter summary 1. So this is the end of this part of chapter summary 1. Thank you. Thank you very much. So if you have liked the video of today and want to support Solved by Hand channel, click on subscribe button here. So you can go to, for example, you go to the video. For example, this is one of my previous videos. You can go to the video and you can click here on subscribe. So you can click here and subscribe. So this is the subscribe button. So you can click here and you can subscribe to support our channel. After subscribing to Solved by Hand channel, you will start receiving notification whenever a new video is published by Solved by Hand channel. Also, you can like the channel, so you can go here, so you can here and you can click on like. So you can click on this hand and you can like the video. So also you can like the channel by clicking on the like button. And if you want to share this video on the social media, you can click on the share button. So you can go here and you can click on share. For example, you can share the video on WhatsApp, on Facebook, on X, or by email, or also so on LinkedIn, whenever. So you can share the video just by clicking on the share button. Also, whether you like or dislike the video, please leave a comment. So you can leave me a comment. You can go here, so you can go here. So here, so if you are logged to your Gmail account, you can go here and you can add comment. You can write a comment here. You can go and write your comments. And I will be very happy to hear about what you think about my videos. So please leave a comment whether you like the videos or you don't like them. Just write a comment and let me know, and I will be happy to know about your opinions. Lastly, I want to show you that there is a second way to subscribe to Solved by Hand channel. You can click on the watermark. So for example, in this video or on all my videos, you can click on the watermark. So there is, in every video there are watermarks. For example, you can click on this watermark. You can click here. If you click here, you can go to this page and you can click on subscribe here. So you can here, this is a second way of subscribing to our channel, so you can subscribe here. Also, just put your hand on the watermark and you can click on subscribe here. So subscribe, you can click on subscribe here. So this is a second method or second way of subscribing to our channel. So that's all for today. Take care and see you next time in another video of Solved by Hand channel. Goodbye and thank you.